Hi everyone, it's Mr. Wilson, and we're going to do some week 8 problems. So I'm going to do two regression problems and then one chi-squared problem. So first one I'm going to do is number 5. The table below show data that has been collected from different fields from various farms in a certain valley. The table contains the grams of raspberries tested and the amount of their vitamin C content in milligrams. Find a linear model that expressed vitamin C content as the function of the weight of the raspberries. So I need to put the grams as my X and the vitamin C content as my Y in a regression calculator. So I'm going to open that. This is the Module 8 lecture videos. We want this one, the equation of least squares regression line. Let me move that over a little bit. And I'm going to pause the video right now while I copy over the X values and Y values. Okay, I have my X values and Y values copied in. So I'm going to scroll down. I don't need to put anything in the estimate box, and I want to calculate the regression equation. So this is it. In our answer boxes, we only have to round to 3 decimal places, so we just want y equals 0.453x. Let me get that in. 0.453x, and my y-intercept or b value is minus 13.332. So I do need that minus sign in there. Alright, so we have part B to this question. Answer the following questions using your unrounded regression equation. If we test 120 grams of raspberries, what is the expected vitamin C content? So when it says unrounded, it means that you really shouldn't round in the middle of a problem. So it wants us to take the full regression equation from our calculator. We're going to plug in 120 grams for the raspberries. The raspberries are X variable, and then solve for Y. So let me copy that over, and then we'll do a little algebra and solve. Okay, I have that copied over from the calculator. We're going to plug in 120 for X, so we just have to do a little algebra. The order of operations says we have to do multiplication first, so 0.45357 times 120 is 54.4284, and we're going to subtract 13.33214 from that. That's 13.33214, and I'm getting 41.09, and then some more decimals, but we just need to round to the nearest tenth for that one. So tenths place would be 41.1. Alright, let's try the next one. This one's a little tricky with the setup, so I definitely wanted to do one of these examples. The table below shows C, the number of thousands of state-registered automatic weapons, and F, the number of murders per 100,000 residents for several northwestern states. So the C's are kind of like our X values, the F's are our Y's. Using your calculator, do a linear regression expressing the number of murders per 100,000 residents as a function of the number of thousands of state-registered automatic weapons. Also give R and R squared. So the tricky part of this is it wants it in function notation. So the function is the y value, it's f, and function notation, I don't know if you remember from algebra, we'd have the name of the function, and then in parentheses would be an x value. In this case, our x value is c, so it wants you to start it off in function notation as f of c. Alright, so we're going to round to 3 decimal places, so I'm going to pause and put the x values and y values into my regression calculator, and I'll be right back. Okay, here are my x values and y values. I'm going to scroll down to calculate, and here is my regression equation. We just have to remember that the y hat here is our f of c, and the x value is our c. So I will copy that over in function notation and pause while I make those changes in our problem. Okay, so here's my function. F of c is equal to 0.868c plus 3.99. I believe it was 3.9895. So when we rounded to 3 decimal places, it's basically 3.990, but we're not going to write that trailing 0. All right, so we also need r and r squared here, so we're going to have to use the other calculator for that. I'm going to go back to my lecture notes, and we want the correlation coefficient, or R. Same thing, we're going to copy the x values and y values in here. I think the easiest thing to do would just be to go back to our previous calculator if you have that tab open, and now we can just copy paste. Calculate R. So R is 0.9989, so it's very close to 1, which means the scatter plot of our data values would be very close to a line, and that means that the variables are very closely related, or the x value is very good at predicting the y value. All right, so R is 0.9989. So if we round that to 3 decimal places, that's just going to be 0.999. So let me go back. And then our R squared value, I'm just going to use the original 0.9989 and square it to get my R squared. Rounding to 3 decimal places there, we're going to get 0.998. All right, now we just need to use our regression equation to do some predictions here. It's asked for how many murders per 100,000 residents can be expected in a state with 9,700 automatic weapons. So the C value is the number of, or thousands of automatic weapons. So we're going to plug in 9,700 for C. And we'll get F of 9,700 is equal to 0.868 times 9,700 plus 3.99. You plug that into my calculator. 0.868 times 9,700 plus 3.99. And it says round to 3 decimal places. Oops, made a mistake. So 9,700 automatic weapons. Have to be careful here. C is in thousands of automatic weapons, so that's why my answer looked kind of strange. So if we want to express 9,700 or 9,700 in terms of thousands, it's 9.7 thousand. So that's what we really need to put in as our X. So let me do my calculations again. And rounded to 3 decimals, this is going to be 12.41. Again, 410, but I'm not going to write the 0. All right, next one. Using your linear regression, how many automatic weapons would be expected in a city with 8.4 murders per 100,000 residents? So this time they're going to give us the Y value, or the F of C value, which is 8.4. And now we have to do a little bit of algebra to solve for our C values. So we still have 0.868 C plus 3.99. Just back to algebra 1, we want to solve for C, so we need to move the number over to the left side. So we're going to subtract 3.99 from both sides. When I do that, I get 4.41 is equal to 0.868 C. Now, to get rid of that multiplier, we just divide both sides by 0.868. And we get C is equal to 5.08. It just wants to round to the nearest whole number, so we're going to put 5 there. All right, so moving on to question 14. This is our chi-square problem. You want to see if a card dealer is favoring one suit over another. You observe the dealer pick a card, put it back in the deck, shuffle, and then repeat the process 388 times. The results are displayed in the table below. Use an alpha equals 0.05 significance level, and complete the rest of the table by filling in the expected frequencies. So we've got our frequencies 110, 86, 103, 89. So we are just taking a card out of a deck, or the dealer is taking a card. We're noting its suit, spades, hearts, diamonds, or clubs, putting it back in, shuffling, and then taking another one. And we're doing this 388 times. So what we would expect is that if it's a fair deck, or if it's a normal deck, that we'd get about the same spades, hearts, and diamonds, and clubs. We know that if we actually did that in real life, we probably would not get all of the suits exactly the same. But our expected frequency, we would just have to assume that they would be all the same. So 388 times, we would just divide that number by 4 and expect we would get 97 of each suit. So what our chi-square test is going to do is going to tell us, okay, could this happen by chance? Could we get 110, 86, 103, and 89 as our result, assuming that we have an actual standard deck here? Or are our results so strange or so unusual that we would suspect that the dealer is giving us a bad deck that has maybe more spades or diamonds in it than hearts and clubs? So what is the correct statistical test to use? This is the chi-square. What are the null and alternate hypotheses? So the null hypothesis is that the distribution of suits is uniform. That means that we would expect all suits to have the same number of cards, and it's a fair deck. So each of the cards, or the drawing of the cards from the deck, those are independent events, but it doesn't really have to do with our actual null hypothesis. So our alternate hypothesis is going to be the distribution is not uniform, or that we would have enough evidence to suggest that the deck is not standard. All right, so let me pause while I get ready to use the calculator. Okay, so we're going to click on our chi-square goodness of fit test. It wants the categories first. So I know my categories are just the 4 suits of the card deck. So spades, hearts, diamonds, and clubs. I'll fill those in. Click next. Now it gives us a box for the observed values and one for the expected values. So I will pause while I get those in. So here they are, 110, 86, 103, 89. For the 4 suits, our expected values are 97 for each one. And we wanted the 0.05 significance level, so I will calculate, see what we get. So this is our test statistic, 4.021, so I will fill that in. Oops, we want degrees of freedom first. That's always 1 less than the number of categories, so that's 3. 4.021. Now we need the p-value. So here's our p-value, 0.25925, so I'll take that back over. Was it 25? 25925, so we want to round to 4 decimals, so that 2 is going to round up to a 3, 0.2593. So our significance level is just 0.05. This is much greater than that. So our p-value is greater than the significance level. So when that occurs, we would always do not reject. So we would say there is not enough evidence to say that the null hypothesis is not true. We can never say for sure that we prove that it is true unless we look at the entire population, but we never have the time or the resources for that. So the final conclusion is, out of these choices, if we're do not reject, we would never say there's sufficient evidence, so I will take care of that. There's insufficient evidence to conclude that the distribution of suits is not uniform. Remember, it's the null hypothesis that we're saying there's not enough evidence to say that it's not true. All right, we got through some pretty tough problems. Again, if we're relying on those calculators, we can take care of the computations easily. And that's it for week 8. So thanks for watching, and good luck on that final exam.